Okay, the recording started. Welcome to the Air Sea Fluxes from Space webinar series. Today, we're fortunate to have Qiang from the University of Chicago, who's going to talk about predicting out-of-distribution gray swan extreme events with machine learning. So giving us an AI perspective on weather forecast and weather forecast capabilities for air-sea interaction events. And I'll let you take it away.
Oh, thank you, Sarah, for the introduction. I'm happy to talk about research. And as I mentioned in the talk, this is still ongoing work. I would like to have more discussion with all the people that are interested in starting AI models and extreme weather events. Uh, so this is also kind of informal talk, to feel free to ask any question if you have during my talk. So what I plan to talk is how the AI models handle the extreme events. Particularly, we are going to talk about this gray swan extreme event, whereby gray swan we actually mean some event that's possible, but probably have never happened in the history or in the training data sets of the AI models. So the picture I asked ChatGPT to plot a picture of TC Heat, California. This is what it gives me. It looks pretty cool. So I'm using it as a background. You can see this would be some event that's possible, but probably have never been happened in the past 100 years. We actually never observed anything like a strong hurricane that hitting California. But theoretically, this event is likely to happen in the future. So if indeed there will be an event like this, how will the AI models respond? Will it capture this event or not? Which is very interesting thing to explore. So I'll start with the interest on extreme events. So NOAA do statistics every year, and they just check the billion-dollar weather and climate disasters that happen each year and do a counting of them. So basically, you can see there's clearly a growing trend of extreme events happening and climate change. Between 1980 to 2024, the annual average would be like 9 events with an economic damage of $62 billion. But in the past 5 years, between 2020 and 2024, there are an average of 23 events with an economic damage of $150 billion. To make the number makes a little more sense, the NSF geoscience total funding usually is around $1 billion per year. And now it's possible that we got even fewer money. Uh, imagine if we can sort of using AI models or other new techniques to help reduce even like 1% of the total damage that caused by extreme events, then it's actually more effective in reducing the cost or saving more money. So the challenge of predicting extreme events is basically because the extreme events are inherently multi-scale in nature. You can see from the small scale, you can find tornado events, and then larger scale, you can find a squall line and tropical cyclone, of course, which we are talking about today. And on an even larger scale, I know the atmosphere river, which has a huge influence on the California. And on a even larger planetary scale, we have unsolved events that can significantly affect the global weather system. So to predict this, the traditional way of doing this is just using numerical models. We have uh, developing a general circulation model to do this by applying the physics law, governing equation, solving the governing equation. We first to discretize this equation and making the model that covers the entire globe. But doing this will require a huge amount of computing time. To fully resolve all kinds of extreme events, we also need to enhance the horizontal resolution of these models. There have been continuous efforts on this, and the resolution of the kilometers have evolved from about 500 kilometers to around 100 kilometers or even higher recently. Here is just a brief work on this at GFDL, which I was a postdoc there. So in the past 40 years, there are on order 10 to the 6 times more computing power. We have more computing power than 50 years ago, and we see a steady growth, a steady improvement of the weather forecast scale in the past 30 and 40 years. So Suki Manami, who is currently still at GFDL, he also won the Nobel Physics Prize in 2021 for solving the climate this really complex problem using numerical models. However, 100 kilometer, which is the resolution we have right now, is still far from resolving all kinds of extreme events in the observation, like tropical cyclone. Basically, people believe if we want to fully resolve tropical cyclones, we need to have a resolution that's at kilometer scale or even smaller. But going from 100 kilometer to 1 kilometer means we need probably 10 to the 6 times more the computing cost. Uh, to make this number more meaningful, the cost of running a 100-year GCM resolution at 100 kilometer is probably only enough for running 1 hour simulation at 1 kilometer, which means our current computing power is still quite far from getting there. And we can see this picture that really to resolve this small scale, like even the TC Hurricane Andrew in 1992, the entire core of this TC is less than 100 kilometers. So we really cannot using any of the GCM at 100 kilometer resolve and expect them to be able to resolve TCs. And even at 1 kilometer, you can see a very rich structure for the clouds. So this has been a problem, and we have sort of at a point that we are thinking, people are starting to thinking what we should do, what should we do next. So instead of just waiting for we have enough computing power, people have been proposing to using AI model to do this. One reason is AI model can run much more faster than the GCM. So again, in 2024, the people that proposed using the AI has also won this Nobel Physics Prize in 2024. So basically, using AI to solve weather problem is a very new thing, but people have already seen a huge improvement on this. So in 2022 here, FocusNet is first proposed to using a global neural network to solve the global numerical global weather forecast prediction. What we do is just using a huge neural network to replace the governing equation of the models, so that people, instead of solving the governing equation, we just evolving the neural network with time and doing that auto-regressively. So we focus the weather 6 hours later from now, and by doing that step, and we get the weather forecast of a few days or up to 10 days, 15 days. And this FocusNet model, here shows a movie of this model. At the top, you can see a focus of the FocusNet, and at the bottom is the corresponding observation or realistic product of AR5. Because they are already, with FocusNet, the model are doing a very reasonable job of focusing weather up to 3 or 4 days. And this is probably in 2022, FocusNet is still like state-of-the-art AI models. But just 1 year, and with this, people have been spending more time and efforts on this. And there's a newer state-of-the-art AI models like the Penguin model, which is proposed in 2023, using 200 median parameters and transformer architecture. And the most recent graph cost model that published on Science using 300 million parameters, showing even better performance than Pangu and FocusNet. And European Center, they also seen this as a huge opportunity using AI model to replace their numerical model. They probably have the best numerical model in the world, but they are now developing their own data-driven AIFS AI models right now, and they have been doing their validation showing that for the metrics, like for global metrics like anomaly correlation coefficient, you can see the AIFS is doing better than the IFS, which is the best numerical model. It probably provides half a day advance compared to the if you compare the AIFS, which is blue curve, and the IFS, which is the red curve here. Everything is evolving so fast. This is something I want to mention. In 2019, people in a workshop, people are still thinking about the idea of using neural network for weather prediction, and they probably think that it's still like 10 years away from we have something that close to IFS. But in 2022, FocusNet already achieved that, and 2023, IFS is sort of beat. So now with AI model, people can actually have a very good weather focus in terms of the metric that most weather center use. Now, and people are still started thinking with this success, people are starting how about using AI weather models for climate research, and especially for climate extreme events. And there are also different groups working on it, and University of Chicago, as I'm currently in, and they also have an AI for climate initiative to do this using AI model to on the climate research. So, but to use AI model for climate, we basically need to have a few requirements to do this. First, we need to have a stable, physically consistent long run on climate scale. Previous weather model, they only ran the model for up to like 15 days, 20 days. But for climate, we need to be able to run the model stably for 100 years, even 1,000 years. But another thing is to train the model for weather model. Most people use just ERE file, which is have like 50 or 40 years data set. This is probably good for weather, but when we're thinking about climate, 40-year training data is really short in terms of when you consider decadal variation or even longer ocean circulation. So can the model capture that event that's not in the training data set, or whether extreme event that had a return period of more than 100 years, like the TC heat California scenario, will the model be able to capture that, given that this training data set probably don't have events like that? So this is another question that we need to solve. So first, about the stability part. There have been proof showing that many of the AI models actually are not stable if you run them for longer term. Here, I just show one example of the FocusNet. If we run FocusNet model, here we show the movie of D500. After 20 days, you can see the model start to blow up. And then it will become sort of meaningless if we use this model for climate research. This is after further examination, what we found is not only FocusNet, most of the current model also have sort of this issue. Some model, if you run them for longer term, like FocusNet, like this Pangu 1 hour version, and they will just blow up after 15 days or 20 days. And even with GraphCast, which is the best model out there, to be able to run it for more than 100 days, we actually did some modification to the GraphCast code so that it can be run for longer than 100 days, but we didn't touch anything related to the model. But still, after running 100 days, the GraphCast model will become unstable. So there are some stable models, weather models. If we run them for longer term, they will be stable. They won't blow up. Like FocusNet version 2, that use spherical harmonic to learn. They are stable, and some variation of Pangu model are stable too. But if you check the climate behavior, when you run the model for multiple years and do an average, you will find they will give you something that not really physical. They will give you a strong jet in the tropics instead of extratropics. The location, the altitude of the jet is also wrong. So these are stable, but they are really not physical if you consider the model, running the model longer. And this is sort of a universal problem. What we found is almost all the models, they have this problem of spectral bias. If you plotting the global spectrum of these models, here I show the FocusNet result, you will see the spectrum of the wind is really not something that's physical. If we check the power, you can see it will get a lot more power at grid scale, which means it will give you some grid scale noise. But at sub-synoptic scale, you will see a lower power there, showing there are some blurring at sub-synoptic scale. So this is a similar issue with all other models. And to solve this, we show that with an even simpler system, we can find this problem with neural networks. Here we just show a UNet. On a QG, you still see this kind of spectral bias, which the blue color here, the blue line here is the UNet spectrum, where the black is the truth. By adding a spectral loss function, and when training the models, we were able to make the spectrum of the model, which is the red color here, that match the observation. And by doing this, we sort of achieve a stable models for the QG system. We see that at least doing some modification of the learning strategy, we can sort of be able to resolve the stability issue. And there are probably other people are often realizing this issue, spectral biasing. People have been working on different approach to do this, and they show that no, we some center they can have a stable climate emitter right now, and they are emerging. But whether this stable emitter is physically consistent, as I showed, if you run them long time, 100 years, 1,000 years, will they give you realistic statistics? This is still something that needs to be investigated. I just show this model, which is an example of the stable climate emulator here. And they are doing fairly good job in stabilizing the model. Another issue, as I mentioned, even if we have a stable model, still some of the extreme events, if you have 100-year return period, they are extremely rare and they do not belong in the training data set. Which is the definition of the Great Swan events. So if all the models are trained with only 40-year ER5 data set, how can we guarantee that they can replicate anything that has a return period of 100 years? If they cannot capture these Great Swan events, which is also called record-breaking events, then it's sort of like have a less power, or we feel like we cannot really trust this model to run them for 100 years and 1,000 years to do some kind of climate research. So this Great Swan definition is proposed by Lin and Emmanuel. They just on contrast with the Black Swan event, which is totally unpredictable. But Great Swan should be, if you have a model that captures the full physics and capture everything, the model should be able to forecast this Great Swan event because it's very likely to happen in the future. So we just examine this using the FocusNet model, and we check the tropical cyclone at the beginning of this kind of study because people are familiar with tropical cyclones, and this is the thing that's easier for people to understand. So first, we evaluate the focus performance on the strong tropical cyclones within the ER5 dataset. Here, the black line is the evolution of the mean sea level pressure of the TCs in the ER5 dataset of 20 category 5 TC we picked in the ER5 dataset. And the blue line is the prediction of the focus net. You can see while they are generally a low bias of the intensity of the TCs, FocusNet did a reasonable job in capturing the evolution of the TCs. So what happens if we remove the strong TCs from the training data of FocusNet and train a new version of FocusNet from scratch? Can FocusNet still be able to predict strong TCs? This is our question, which help answer if we have something really not something not present in the training data set, can the model still be able to capture that in the future? So to resemble this, we just remove strong TCs from the training data set and we see whether the model can capture them. There are different opinions on this. When we started the work, people think AI model is really not something designed to do auto-distribution generalization or extrapolation. So many people wouldn't think this will work. But there are other people think this might be something that worth exploring because what we think of the AI weather models, they are not just memorizing what we provide to them. Some models can actually show the ability of learning dynamics from the model. So there are some evidence showing that even you provide something that not seen by the model, it can still provide meaningful results. So there's a possibility that FocusNet might learn unseen category 5 TCs, gray swans, from the weaker TCs in the Trinity set. By removing strong TCs, we here remove everything that category 3 to category 5 TCs in Trinity set. We only kept category 1 and category 2 weak TCs in Trinity sets in our experiment. So we also here just a plot of the statistical mean sea level pressure. What we do is we basically, to make things simpler, we only remove the TC that has a mean sea level pressure that lower than 988 in the training data set, so that resemble the strong tropical cyclones. We have one version that trained with all the data we call FocusNet full. We have the other version trained with a strong TC removed from training data set. We call FocusNet no TC. And because we remove strong TCs from the training data set, we sort of have less samples, less training data for the model. Then to make a more fair comparison, we do another run, FocusNet random, by randomly remove some of the training data set from the FocusNet full. This random means while it's sort of random, but we kept strong TCs in this FocusNet random experiment. So both FocusNet full and FocusNet random have strong TCs in their training data set. FocusNet no TC only has weak TCs in the training data set, but do not have strong TCs. So these are the difference. In terms of training data size, FocusNet full have the full data. FocusNet random and FocusNet TC have less data, like about 75% of the training data set. But these two, FocusNet random and FocusNet no TC, have equal number of training samples to both models. So these are the controlled experiments we run for doing this experiment. We then test all versions of models. For each version, we train 5 different relations starting from scratch to show some model uncertainty. Then with all these different versions, we test their performance with strong TC in the test data in the period between 2018 and 2023. So here just one example for Hurricane Lee in 2023. It turned out by removing strong TCs from the training data set, then the model failed to get that Hurricane Lee. You can see the prediction, both for FocusNet 4 and FocusNet random sort of capture the evolution of the Hurricane Lee reasonable well, only that there are maybe 1 day delay, less than 1 day delay in the prediction. But still, the evolution of the mean sea level pressure, which is blue line here and light blue line here, they resemble the true data of the which is the black line shown here, or Hurricane Lee. But if we check the prediction of FocusNet no TC, then we find something dramatically different. FocusNet no TC, instead of giving us intensifying TC at the beginning, it gives something that will weaken the intensity of TC at the beginning. Then the TC try to intensify maybe a little bit, but the intensity of TC is still very weak. It's on the order of category 1 or 2 TC rather than a category 5 TC as is shown in the observation. So FocusNet no TC will still focus a TC, but it will focus a very weak TC, which is something worse probably because this is kind of false negative. So it will show that there's a TC, but the TC is very weak, so no need to worry. But while in the reality, the TC is really a strong TC that will cause lots of damage. So we not only tested on one single TC case, we tested this different version of the model on all 20 TCs we find in the test data set of 4-year, 6-year data set. So you can see they all show very similar picture. Both FocusNet 4 and FocusNet random with strong TCs in their training data set, they are able to capture the evolution of strong TCs, while for FocusNet no TC, it will only predict weak TCs instead of strong TCs. If you initialize the model from a very weak phase, very weak stage of the TC, it will intensify a little bit, but it will just tell you this is a weak TC. After some 1 day, it will stop intensifying. Even when you provide the TC that's really strong at the beginning in the initial data, the TC is already very strong. When you feed that to FocusNet no TC, it will further weaken the TC instead of keep intensifying. It will keep telling this weak TC instead of strong TC. This is true for all 20 cases, and we examine even individual member doing ensembles wouldn't help with this. In general, FocusNet will give you a very weak TC. Some of the members give you an intensity that's stronger, but because the model is becoming unstable, it's not a physical value. It will give you some low value, then after 1 day it will just blow up, which is a blow up signature, not a intense TC. So we show that actually if we use FocusNet for TC, then FocusNet wouldn't be able to capture a global gray swan. If it had never seen a strong TC in the training data set, then it won't be able to capture the TC. Then some might wondering that how about if we show some TC in the training data set, but instead of remove all the TC from training data set, we remove only basin-wide. Like we remove only strong TC in the West Pacific basin, what will happen? And we did experiment like that, where we sort of only remove strong TCs in the West Pacific basin only, and in the North Atlantic basin only. Basin-wide, we remove strong TC and test the model performance on that basin. So we see that the model can actually transfer learning in one region to another by learning from similar events. Like even if we remove all TC in the West Pacific basin, the model can still learn from tropical cyclone in other basin And then when we test the model on the West Pacific, it was still doing much better performance than focus than no TC. The pink line here in plot show that if we remove the TC, strong TC in the West Pacific only, it will still give you an intensified TC. Especially you can see clear here, the model will learn from TCs from other basin and will predict intensifying TC rather than just weakening in focus net, no TC. A similar picture for the results in the North Atlantic Basin. Basically, the model was able to learn from events that happen in other region, but apply the knowledge to a different region, different basin. And this is sort of encouraging, showing the model is not really not only memorizing things, it's actually can learn something across different basin, while it's not be able to do extrapolate globally, it sort of can do some generalization across basin. So this is something really encouraging we found. To verify this, we also test another cases like this Dubai event. In 2024 April, Dubai region actually has a strong rainfall event that lead to a severe flood in that region. One station in Dubai even observed over 200 millimeter of daily precipitation that single day, which has never been recorded and is an unprecedented event since the record there in 1949. So this is a regional Great Swan event that never happened in that region, but probably similar events because that region is a desert, and Dubai is a desert region, but it probably happened in other regions. So we check more on that event. For the Dubai event, if we check Dubai event, Dubai region only, that event in air file, it will give you 60 millimeter rainfall in 12 hours, which almost doubled everything Dubai has seen previous in the training data set. But if we check globally, then Dubai event is something rare, but also happen in other regions. This is showing the PDF for the entire Northern Hemisphere. You can see Dubai event is a rare event, but it can be seen in other regions. So we check different model performance for that event. We see that GraphCast actually doing a reasonable job in capturing that Dubai event. So this is black curve is real-nice data in the AR file, where the blue curve is the prediction of GraphCast. The dash line is the maximum in everything it has seen in the training data set. Still, GraphCast was able to predict or doing sort of extrapolation over this threshold, giving something that had never happened in the region but happened in other region. This is another proof that showing the model can learn from different regions and apply it to a new region. We did a bit more exploration on this, showing the model while predicting this event, while trying to predict that event, and this is the effective receptive field of the GraphCast when it makes Dubai prediction. You can see it actually use information from global. It's just a receptive field of different variables. All the variables have a global input. It will use global input when it infers the Dubai event, showing might be the help with the learning from different region. So based on that's give you a take-home message or a summary of the talk I did today is we really need to have a better understanding of AI models for extreme events because they have outside effects. What we found is FocusNet cannot predict global great swans. They cannot learn from weaker events and do extrapolate, but they can predict regional great swan, meaning they can sort of transfer learning or translate learning of dynamic similar events across different regions. So this is encouraging, is something probably worth more exploration. And this kind of study has probably important implication for other AI models or AI climate emulator when you try to run the models for 1,000 years to solve internal variability uncertainty of strong experiments. But you need really first to make sure that your model are capable of doing that. If you run model 1,000 years, you want to make sure the model is producing something reasonable for events that only happens every 100 years. Definitely, we are still working on this topic, and there are future work warranty for the AI innovation to better handle these extreme events. I'm also happy to discuss any of this related topic on how we should use AI models and for extreme events detection or prediction. Thank you. I think that's all my talk today.
Well,
But
thank you so much for this super stimulating talk. Questions for Qiang? And maybe while people are, oh, I see Yolande Sarah has her hand up. Go ahead. Go.
Hi, thanks a lot. Yeah, nice talk. I wondered, and I don't know much about these AI models. So, but when you remove the events, I'm wondering how sensitive it is to that methodology. Meaning, could you actually be training it not to create an extreme event under conditions that normally did create a hurricane, extreme hurricane, if you don't remove the event properly? Like, how far in advance do you remove the data, or if you're just smoothing the data? Do you understand what I'm saying? So if we don't quite understand what creates an extreme hurricane, maybe you've left in things that taught the model something we didn't want to teach it.
yes, I totally agree. We actually had lots of discussion on how do we do the removal of this kind of study. I totally agree with you. This is very critical. We do not want to mislead the model for something we wrong that give you the wrong impression. We want to make sure everything we fit to the model is correct. So by doing the removal, what we do here, we choose something simple. So if there's a TC that there's a strong TC in the training data set, so we will check how strong it will evolve eventually. So if it reaches a strong intensity in the lifetime, then we actually just remove the entire data for that TC before it even going to the strong TC state. But what we feed to the TC is still completely reasonable data set. The same data set we use for the FoxNet 4. It just has less data that it doesn't contain the time period where it becomes strong. So all other data, if there's no TC in that day globally, then we also just use that data set. If there's a TC in that day, if the entire lifetime the TC is weak, we do not remove anything. We just feed that to the model. But if the TC becomes strong in certain day, then we actually further remove more data containing even a little bit more, because FoxNet actually using actual time step for fine tuning. So we actually remove a bit more just to avoid there's no strong TC in the training set. It will not use any information from that, but the entire period is removed when the TC is strong. So it's possible that still day one, day two, the TC is very weak, while later it will become a very strong TC later, but we only keep maybe day one, day two for that TC, well, this week. Yeah, we test a few, we are only using mean sea level pressure, but we test a few things, everything is very consistent with this. Yeah.
Other questions? So maybe I can ask a hypothetical. You test on category 5 data, but you remove the equivalent of Cat 3, Cat 4, and Cat 5. What if you tested on Cat 3 or Cat 4? Would that be as bad?
Uh, we we probably need to do that systematically, but I did tax a weak
Mhm,
TC.
mhm,
So when we tax weak TC, the category 1 and category 2, these are the FoxNet notice will do as good as FoxNet 4 and FoxNet Red. So
mhm,
when the TC is weak, the performance of all different models are just similar.
Mhm.
It will just not, it will still, for weak TC, this model is still doing okay. For category 5, it's total disaster.
Mhm.
But for category 3, on the marginal, I would expect something better performance, but not as good as
Mhm.
FocusNet 4. Yeah, it's probably in the middle, but we need to do more systematic evaluation on category 3 or category 4. Yeah, to answer that question properly. Yeah, this is a very good question. Yeah.
Other questions? Rick, go ahead.
Yeah. Hi, Qiang. It's great work. I don't know if you can. Okay. Can you hear me?
Yeah, I can hear.
Yeah, just a question on your loss function. You said you used spectral regularization. Did that impose any sort of constraint on how deep the cyclones could be? If you, I mean, I know people are doing experiments. Subic is one. Trying to get those low pressures by changing their loss function. Maybe it's something you could comment on here if you could. Thanks.
Yeah, I agree. By the way, we are not using this spectral loss for FocusNet. We are just using the regular FocusNet training with our test here. We did not apply anything spectral loss here in this model. What I showed is by doing a spectral loss, we were able to make a simple model like for the QG system, we can achieve a stable simulation. But we didn't test anything here on FocusNet because even use a regular MSE type loss function, the FocusNet 4 will just give you a reasonable work on predicting the intensity of TC in ER5 world, not realistic TC. But if we remove training diff, everything is the same with FocusNet Notice and FocusNet 4, except the training diff is different. So I do not think adding a spectral loss will solve this issue we show here because basically there's no thing as a strong TC in the trend list focus no TC here. You cannot just by modifying the loss function, you need to have some data there. Then probably adding more weights to that kind of data, doing some weighted loss function so that the model will learn more towards some extreme events in the training set. But the FocusNet no TC, there's no trend, basically there's no extreme events or there's nothing Grease Swan in that trend data set. So you cannot nudge the model towards that part of data because there's no data there.
Totally.
What
Yeah.
so is if you have no data, then the model will definitely not work, even what kind of approach you want. But if you have like very small, a very rare events, like very small portion, a small portion of that data, it might work. As what we showed in the West Pacific and North Atlantic, if you just remove something in one basin, then you might be able to further improve the performance of this model by making the model, nudging the model towards some strong TCs in other basins or everything,
Mhm.
or things like that. But if there's no data, then your model probably won't work. But yeah,
Yeah.
changing the function. Thank you.
That's a good result.
Other questions? Maybe I'll ask, I think that the ERA5 data, when people compare with scatterometry, they find that it misses some of the most extreme events that appear in some of the scatterometer products. And so there's a potential that even training off of the forecast, the best available forecast, it's missing some of the strongest peaks or troughs in weather events. Any views about that?
Yeah, that's totally true. And people have been I didn't do the work, but people have been evaluating the models collinear focal nets graphical Pango models on the real world TC but compare their performance in the observed tropical cyclones, and what they found is they are just pretty very weak TCs in general because the AR5 dataset itself will give a weak estimation of the TC, because the
Mhm.
data quality has some issue, so that the model will not predict the TC in the real world very well, the intensity. But they do show that FocalNet is doing as good as other models in that test in capturing the real world TC. But what you mentioned is true because AR5 data, as I sort of show that we only have AR5 data is the best data we have for training the model, basically. That's why people are using the model, using the data, but the data itself has problem. It won't capture the intensity of TC. The rainfall product, the precision product of AR5 also has a problem. It won't have very extreme rainfall in this set. For the Dubai, in the vision, we have like 200 millimeter, but in our AR5, it only has 60 because cost reduction and other things. But people have been sort of trying to thinking about this and trying to correcting this, and by training the model on AR data first, then sort of fine tune the model with observation data. If you have rainfall products, I know like NeuroGCM, they are fine tune their model with the true satellite based observation, and to further fine tune the model on some extreme rainfall products, and which is very good work, I think. And how satellite observation can help with the development of the AI models, and this is definitely one future direction that people should be thinking about. Uh, but I totally agree with you. This is a great question. Yeah, great point.
I'm glad you mentioned that. This is obviously a webinar series that's focused on observations, and so people are looking to really understand the role of observations in new strategies for analysis and
Yeah.
thinking
Another thing
about where the observations are most useful and what observations are needed.
Yeah, I probably should have mentioned, but another thing I think very important is how do we benchmarking our AI model? Basically,
Mhm.
all AI model are training with different loss function, different approach. They have similar approach, but they have kind of different goal or loss function in their mind. For this model, they are trying to do global weather forecast up to 10 days, 15 days. If you check ACC, root mean square error, they will give you better score in terms of scorecard. But if you evaluate them on some extreme events, these AI models are still probably not achieving their best potential yet. So I think benchmarking the AI models against some specific extreme events is still very useful and very meaningful to do. It's even critical for improve their performance for these extreme events. Um, Regarding that, observation is probably the best we have. Just to trying to match the AI models, match their performance against the observation instead of AR5 data. I think this is the correct way to do. Yeah.
Any other questions? If not, I'll keep asking. I have one more. Um, so I guess one of the challenges is we have physics-based models, the classic ERA5, and you have the AI approach. Is there any prospect for merging those to be able to pick up more of the physics that goes into an extreme event, even if it's not in the training data?
Yeah. That's kind of our proposed way to solve this issue. Because we cannot do if there's no data, we cannot do much. What we show here is if you don't have data, you cannot do much. But then something you can think of is how to make data, how to make meaningful data. And physics model is actually one way to make meaningful data for training the AI models. So I think a different group are also thinking along the same line. But this is definitely one future work we are checking right now, and our group actually have people working on that. How do we use physics model to combine physical model to AI model to better resolve this issue? One thing we did check for in this work is actually we try to uh, check how the model is capturing the physics in the current focus net. So for TC, we know gradient balance is one balance that's in the TC. It's often observed in both observation and often showed in the ER5. This is the equation for gradient balance. Basically, the balance between the pressure gradient force, the centrifugal force, and the Coriolis force. So we calculate the when based on this relation we found in the AR file because it's a physics model and there's a good match and you can see sort of gradient when balance in this AR file model. But in the both FocusNet 4 and FocusNet no TC, this gradient when balance is not observed in both versions. Uh, so this is at least something you want to improve for the AI models, and we probably need a better innovation in combine these physics and AI models. Currently, we are training the model without any physics knowledge. Basically, we just provide the data and using mean square error as a loss. But we can certainly thinking along this how to better combine AI model and physics in the training. Yeah.
That sounds very promising. I see Yolande has her hand up.
Yeah. Along those lines, then, I mean, there are efforts, there are models that are more hybrid AI physics models out there that people are trying to develop. Do you think that's also a promising way, or do you think I mean, that's just not going to get us where we need to be as far as you started this talk talking about how inefficient running these models, the physics models are. So I don't know. What's your thoughts on those hybrid models? Like what I think Tapio Schneider is doing. Yeah.
Yeah. I agree, and we actually have a good collaboration with Tapio's group. My Alorda currently, I should acknowledge that. My Alorda is currently Pedram. We are working on cross collaboration with. We have lots of collaboration with Capricorns, and we are using their method called EKI and some common inversion to further fine tune some of the AI models in our group. Not this work, but other work too. And people are thinking along the line. Tapio Snai is doing combine the AI model and the physics models, and the newer GCM, as I mentioned, is Google team. They are just running the dynamic core of physics model and using AI to sort of learn the physics of that model. That's another way to do hybrid AI models and numerical models. So I don't have a like I don't think there's just one way which one correct way to do this. But the more you can make a model have more physics, probably you will get a better model. At least that's my understanding. Uh, in terms of how to do this, yeah, people have different approach and for the newer GCM, what I can see is they have while they demonstrate a very good performance with their hybrid model, but their model also has problem. It's like stability issue, as I mentioned, is one key challenge for their model. They try to run their model. They try a bunch of work probably and to make their model stable, but still their model kind of have stability issue. If you run the model, somehow some members will just blow up for no particular reason. And they are not as stable as the numerical model currently. There's still one challenge they need to resolve. They actually use the spectral loss I mentioned earlier. We were able to make this simple QG model stable in our experiment, but they also apply similar approach for newer GCM. It helps a lot, but it didn't quite solve the model completely in their test. Yeah. So
Okay. And then just a quick clarification. I realized that I was a little, so you're calling that class 5 hurricane in your no TC run a gray swan. Is it a black swan really? Because you still consider them predictable. Is that the difference that you know what I mean? Like, is it that you're actually trying to get a black swan at this point because you removed, if you had left in, have you ever tried just leaving in a smaller number of extreme to make them way more extreme, the class 5 hurricanes, and then trying, do you know what I mean?
yeah, I totally agree. The definition between gray swan and black swan is black swan is something that's totally unpredictable because people wouldn't think about that. I guess the term gray swan is proposed as to define some event that's at least physically possible. We know this kind of event will happen if we just run the model long enough. But we haven't been observing them in the trend data set or in the historic data set. That's why we call them gray swan. So gray swan actually means something not in the trend data set, not in the at least
Okay.
not in the observation currently. Black swan is just totally unpredictable. It's just similar. Probably COVID would be something black swan. I would guess. But yeah, gray swan. That I think category 5 TC, even category 6 TC is still something gray swan. I can imagine that happening in the future. Like TC hitting California while it's not in the data set currently. I would think that will happen, probably in after a few hundred years. That would be a gray swan event instead of a black swan. Yeah.
Okay.
I guess there can be many different flavors of gray.
Yeah.
Yeah. Yeah.
Well, if there are no other questions, we are just about the end of the hour. Thank you so much for a really great discussion. This is
Thank you.
a
Thank you
great
for the
talk. This has
invitation.
been really enjoyable and very
Glad.
helpful perspective.
Thank
Thanks
you
very
all for.
much.
Thank you.